Welcome everyone to the presentation of our paper titled Force Sharing Problem During Gait Using Inverse Optimal Control. I will start by presenting the context and the related work. The hypothesis of optimality of biological motion was emitted during the 20th century. The first computational models applied to human motion appeared in the 1980s with Flash and Hogan. Biological systems have many degrees of freedom, making them redundant and granting them infinite possibilities when choosing trajectories of motion. Trajectory selection is modeled thus as optimization. For example, here is a 6 degrees of freedom stickman performing a box lifting task. Among all the trajectories it could choose from the confines of the turquoise shape, it chooses the red one. Suppose there is an objective function that is optimized to select that particular trajectory. The objective function underlying the selection process can be identified from data, and we call this inverse optimal control. With the optimization problem on one side and the optimal trajectories on the other, we optimize to get the optimal trajectory, what we call direct optimal control, and we measure optimal human trajectories and identify the problem, what we call inverse optimal control. We have been studying the force sharing problem during gait, which is the task of distributing muscle forces to obtain desired torques in the joints. We abstract away the feed trajectory and joint torque planning, focusing only on muscle force sharing when the torques in the state of the body are already known. The muscle forces are related linearly to the joint torques via their moment arms, defined by the geometry of the muscle-ligament joint connection. The illustration is depicting this. We have used open-sourced clinical data for this study, from where we get the reference forces and moments. The force-sharing problem is therefore, from top to bottom, the task of finding bounded muscle forces that produce given joint torques and that minimize an objective function. In inverse optimal control, the objective function is most commonly represented as a positive linear combination of features. We denote the weights of the combination with the symbol omega and the feature functions with symbol phi. The task of inverse optimal control becomes then to identify the weights that make our optimization model best fit the data. The types of features that we use are norms of muscle forces, of muscle activations, and of muscle stresses. Also other functions like muscle powers. Once the data set is ready, we can opt for one of two common methods used in the literature to find the weights of our optimization problem. They are occasionally referred to as the inverse KKT method and as the bilevel method. IKKT attempts to minimize the residuals of the KKT conditions of the optimization problem evaluated at the data. It yields a constrained least square problem which is fast to solve, but it is statistically inconsistent. The bilevel method minimizes the mean squared error between the model's prediction with respect to the data, and it yields a hierarchical optimization problem, which is very difficult to solve but is statistically consistent. We advocate for using only the bilevel method, but we applied the KKT method to demonstrate that it doesn't work for our problem, and we gave a toy counter example to the IKKT method in the paper. So further slides will contain results of the cost function weight identification, as well as the results of the muscle force predictions. As mentioned, I will present the results and prospects for future. So before the results, I want to mention that we separated the analysis into two phases of gait: the stance phase, when the foot is in contact with the ground, and the swing phase, when the foot is traveling along the step trajectory. For each of the 15 feature functions along the abscissa, we find the corresponding weight on the ordinates. We can see that muscle activations and muscle powers are minimized for both phases. These features depend on the state of the body and are evidence of the presence of feedback in muscle force sharing. 35 muscles were considered in the study, with 10 gait cycles in total. The mean and 3 sigma of our measurements are shown as the blue line and the gray area respectively. A concrete trial is shown in black, and its prediction is shown in green. In general, large amplitude muscles were well predicted, while low amplitude muscles not as well. The average error and correlation per muscle are in the vicinity of 170 newtons and 0.7. We also predicted joint stiffness, with results that are quite satisfactory. So for more detailed analysis, please see the conclusion of the paper. Here are tabular numerical results for predictions with IKKT, bilevel, and individual cost functions. Column-wise, you can see the bilevel method gives the smallest error. Row-wise, you can see the IKKT method falls behind. So that's all. In the future, we plan to study the effects of hemiparesis on the objective function retrieval, conduct the study with multiple subjects to see if the findings generalize, and of course use more extensive modeling of the gait by taking into account the step planning, for example. Thank you for your attention and goodbye.